So in fluid mechanics, there's several different ways that we can describe the displacement and the motion of objects, and these are usually referred to as the Eulerian and the Lagrangian description. And there's a very useful film to show this in pictures and movies, which is far better than I can draw on the board, which was made by John Lumley. It's one of the National Committee for Fluid Mechanics movies, and it's available and linked, and I'd encourage everybody to watch this to illustrate some of the concepts that we're going to talk about today. But the key thing that we have to recognize is that there's a couple of different ways that we might describe the motion and the deformation of a small material object. And so that small material point that I'm going to follow is labeled in pink here, and it's what we would call a material element. It's always the same pieces of fluid. And so as it moves through space, it may be deformed, and we'll think about deformation shortly. But for now, at least, I just want to think about the idea that we might be interested in describing where it goes in space as a function of time. And the first way that people will think about doing that is called the Lagrangian description. And the idea is that we'll label our particle. And so we might label our particle x, and so let's label this particle as x, and it's at an initial point in space, which we'll refer to as a vector position x0 at time t0, and then at some later instant in time it's moved to a new position, which will be x as a function of time. And we'd like to be able to describe the motion of all points in our domain this way. So we'll label our particle, which is initially at x0, at t equals t0, and then we'll just follow it forward in time. And so our description would be that we'll specify where it is in terms of some function, and that function is our displacement function. So we'll call that function x to indicate that it is indeed for this material, and it's some function that will say, tell me what the current time is, and also tell me what the initial time was, and what the initial position was. And if you tell me that information, then this function will project this thing forward in time, so that I can tell you what this is at any future function in time. Similarly, so once we know that, similarly, we can then report the property of the fluid, and so any other property, any other arbitrary property. So, for example, we might be interested in the pressure, the temperature, or the pressure, or the density, or any other field variables. So these are these ideas of continuous or continuably differentiable field variables, and we just have to think about them as being functions of this material point and where it is at any future point in time. So we find the position of this, and then we can say that if I know the position of this, I can measure the temperature. And so very commonly, this is very common in, for example, meteorology. When we might, for example, release a weather balloon, or an ocean buoyant tracer to report things like the surface temperature of water or the local wind speed. So that's a very common way of describing things. The difficulty with it in fluid mechanics is that it means that I have to label every single individual piece of material and then project them forward and think about where they go in time. Now, if I was interested in saying where did something come from, I may be able to invert this description. So I may even be able to take the inverse of this function. And so we might be able to, if we were to invert it, we might be able to wind the clock back and say where did something come from, which would be thinking about the inverse of this function if I measure where something is at a present time and a present position. So in principle, that's possible. It turns out to be very, very hard to do, and the whole description of fluid mechanics becomes very, very cumbersome if we try and write things in terms of Lagrangian descriptions. So a much more compact way of doing this is in terms of what people call an Eulerian description. Where we don't worry about the identity of material elements. So basically we neglect the identity because we don't really care. We'll say that every single piece of material, we don't really care about what it is. It's just a piece of fluid that's coming past here, and we'll just label the velocity of points in space and time. So the equivalent of this would be to say that I don't really care about what this material is. What I care about is its velocity. And so if I was to try and represent that, I might say that if I neglect this, I can just say that it has a velocity v, which may be a function of position and time. And the way I'll describe my flow is by not worrying about material elements, but I'll worry about at every single point what the velocity is. And so we'll specify for a series of places everywhere the velocity field. And so our primary variables now become the velocity and the position. And we don't care about the identity of material elements. This turns out to be much more convenient. We, of course, lose track of any individual piece of material, but this is the way that we would typically describe things in the lab. So we'll say this is very common in the laboratory environment. Because it's very easy for me to say, give you a thermocouple and ask you to measure the temperature at different places in the lab environment, or maybe measure the pressure at different places in the lab environment. And of course, eventually we can also measure the velocity in the lab environment. And so things like anemometers, barometers and thermocouples all essentially work by thinking about, or we report the results in terms of descriptions where I've just moved them through space. The challenge is, how do we convert between one reference and the other? And in particular, the one thing that we might be particularly interested in is thinking about the acceleration of a material point. So if I follow a material point that's at a velocity here, when I'm at the new point here, I might be moving at a new velocity v2, which is different from v1. And we're going to need a way of converting between this Lagrangian description of the world and this Eulerian description of the world. And we're going to see that is in terms of something that's called the material derivative, which we can express in Eulerian forms by this. And of course, all this really is, in terms of this, is the second derivative of the position with respect to time. And so this is going to be the most important thing that allows us to convert between the Lagrangian and the Eulerian description. The other one that, of course, is quite simple is to recognize that the velocity at a point is nothing but the first time derivative of this. But the thing to recognize is I'm writing this as a partial derivative in both of these cases. And the partial derivative is there because we have to recognize that we're following a particular material element that we labeled. We called this point x. and it's moving in space and time. And so to convert between this, we'll need this operator, which we will see next time, that we will call the material derivative. And understanding what the material derivative does is very important in allowing us to convert between the Lagrangian description and the Eulerian description.